Bonjour.
Merci. Merci pour l'intro. Hi, everyone. Thank you for the invitation. To shortly introduce myself, I will speak today about the sound underwater in the marine ecosystem. And I would like to say I'm not a biologist, even if I speak about cetacean species or other marine species. I'm expert in signal processing, bioacoustics, and pattern recognition. I'm professor at Sorbonne University in Paris, France, and my 4 projects right now it's about the relationship between mother and calf in humpback whales, social interaction on sperm whale. I also work on dolphins and especially the language of dolphins. And the last one is about underwater soundscapes. We want to describe the underwater soundscapes, and I will go back on this on the next slide. So what is, I think Kelvin says that we can't improve or explain what we can't measure or something like this. And it's exactly what we will do. And today we have a lot of different techniques to measure the sounds in the water, and we use waterproof microphones named hydrophones, and we can deploy the hydrophones from a boat, for example, for opportunistic observation. We can also deploy hydrophone at the seabed or at the sea surface attached to a buoy if you want to record for 1 week, 1 month or longer. And now we used robots to do that. So, for example, we did a project with University of Las Palmas, and we developed unmanned sailboat, and we use a glider, underwater gliders, to go off Las Palmas island to meet some different whales and to measure the density of the marine traffic. And here it's a network of different acoustic observatories in the southwestern Indian Ocean, and probably it's the largest data set of recordings of blue whales and fin whales of the world. Okay, and recently we use electronic device that we can deploy directly on the whales and to measure the sound they can emit, and also all the soundscape where they go. So we go very slowly and carefully, very close to the whales, and with a stick we put the device, and with suction cups they stay on the whales for a couple of hours. And we have also on this device, we have a video cam, and I will go back on this because it's very important to understand their behavior and their vital activities. So what we have to do about underwater soundscapes, in fact, it's more a challenge even today, because oceans are in fact an open space world, and with a lot of different sound sources, and with sounds with the same intensity, the same bandwidth. I mean, it's a mix of different sounds, and it makes it very difficult to extract them and to automatically detect and identify them. The other thing is the acoustic propagation is kind of complex in the water, because the celerity of the acoustic wave is not constant on the water column. And also, it's difficult to compare all the data sets because it's not the same hydrophones, it's not the same recorders, so the sensitivities are totally different. The signal to noise is totally different. The dynamic range is different between, because of the difference of 16-bit, 24 bits, or 42-bit float code. And also because it's not the same area, and we know that the acoustics, the propagation is attenuate different things. The hydrophones are not used for the same objective. And for example, in the Indian Ocean I mentioned before, the objective was to measure the earthquake, and we deturn, in fact, this objective to detect blue whale and fin whales. But the idea is all the data set is kind of data dependent, objective dependent, and is something difficult to use. The last thing is now, in 2025, we can find data set online. For example, Woodsole Institute or Cornell already put data set online, so we can work directly on it. I'm one of the organizer of the DCLDE workshop. It's an international conference, and since 2003 we put every 2 years one data set online and to invite different researchers to work on it. Recently we put data, it's only a cetacean species, and recently we put sounds emitted from the North Atlantic right whales, fin whales, blue whales, and sperm whales. And so the idea is to develop different methods to automatically detect and classify the source event. Okay. So, as you said, they have, in fact, we can try to simplify a little bit the problem and to reference for 3 main classes called geophony, biophony, and anthropophony. Recently, I mean, the main objective of all the different projects right now is to focus on the last class, anthropophony, because we are sure now that the human activities at sea has an impact on the marine ecosystem, and we want to measure it. I put a spectrogram, it's this figure, it's a time frequency representation, and we can see that in the same acoustic recordings we can have different acoustic sources, and the challenge is to detect them. Okay? So obviously, since I worked on this kind of problem in 2000, we switched progressively to acoustic descriptors, the use of acoustic descriptors to AI, especially because we want to have a general classifier now, and the new CNN are give very interesting results. Right now I have a student, Lucie Jean Labadie, who started her PhD last year, and she's the third one to work on this project. Okay, so we want to focus on the human activities, and the idea is because our economic model is to grow all our activities, even in the ocean, and it makes obviously the impact higher and higher. We are not against the human activities, obviously, but we want to try to mitigate, in fact, their impact on the ecosystem. And we have a very nice project. I was last week in Quebec, Tadoussac, because we organized a conference on humpback whales in this area, and ISMER, it's a laboratory from Quebec University, showed a very nice project called Mars. And what they do, they put hydrophones and a video cam just to observe all the commercial vessels in the Saint Lawrence River. Okay, and in France, I think that we have a kind of, and they have a very nice data set, because they can do the link between the vessels and the noise, and it's very important for the ship owners, but also to mitigate the traffic or to reduce the speed of the vessels, for example. In France, I think we have something similar of Marseille, led by the French company Quiet Oceans. They measure, in fact, the noise, continually the noise, underwater noise, and they use IS to know what vessels were present. So all this information, all these measurements are very important, especially to justify or develop new agreement in a local, regional, and international way. Okay, so now we will switch discretely to the cetacean species. It doesn't mean that only cetaceans are impacted. In fact, all the marine species are impacted from the anthropogenic noise, but it's kind of, I mean, we have less publications about fish, about, I think for the krill, for example, we have just one scientific publication up to now, so we have to work a little bit. But the four main acoustic features to describe the impact is obviously the acoustic intensity, the bandwidth, because the bandwidth, the type of the sounds, because it's different if it's a continuous or a pulse sound, and the time of exposure. And so I put and so now we have a lot of different studies about cetacean species, and for example, observations in different areas for different species. At the beginning, late 90s, it was very difficult because all the individuals have a different reaction from these anthropogenic sounds. But now we have a good view of what happened. So we have impact on their auditory system because cetacean species are mammals, so they have exactly the same auditory system as us. They can change their vital activities because, for example, we know that some military sonars are a little strong, and so sperm whales, for example, stop their dives during the exposition of this kind of sounds, and a lot of different situations explain the strandings of different species, especially beaked whale. Okay, so since 2007, the American researchers published a threshold for auditory system of cetaceans, and because they can't do that for the 90 species, they group the different species in three main categories: low-frequency cetaceans, high-frequency cetaceans, and very high-frequency cetaceans. And for each of these classes, they give the threshold that explain loss, auditory loss, permanent or temporary auditory loss. Okay, so now it's kind of now, I mean, when the industry wants to do something in the water, they can measure their activity, their noise that they will produce, and see if this noise will impact or not the different categories of cetaceans. Okay, so let's go to few words about the species. Okay, so 90 species with two main frequencies, mysticeti and odontocetes. They have nothing in common right now except they are mammals, but their anatomy, their size, their behavior, their diets, and also their languages are totally different. And they emit sounds all the time during their vital activities, obviously, and their social interaction. Okay, so the idea, so what we do in our team, we focused at the beginning on the vocal generator of mysticeti, and we explain how they create these different sounds and vocalizations. And it was interesting for two things. The first thing is we focus on every details on this vocalization, especially the non-linearities, and I will go back on this later, and also to explain how all this language can propagate in the same population. Okay, so I choose 3 samples. I choose 3 examples of cetacean species because I can't speak about the 90 species. So I will present 3 species. So let's start with sperm whales. Sperm whales emit clicks. So this sperm whales from off Toulon. Toulon is a city in south of France. So this species, the vocal generator of this species is 2 membranes at the blowhole, and the membrane flap and explains these clicks. And in fact, it's not just one sound, it's a multiple sounds, like you can see P0, P1, P2, P3. It means that one click, it's a multipulse. And the distance between pulses are in fact the length of the head of these individuals. And because sexual dimorphism is very important for sperm whales, we can distinguish if it's sounds emitted by a male or sounds emitted by a female. The other thing, it's they use clicks for echolocation, exactly like bats, and they did exactly the same. They just, at one point, when they want to have acoustic image at what they have in front of them, they can accelerate the clicks, and we call that a creaks. And codas, I will explain what is it for the next slide. And trumpet calls, it's very funny because the first publication about trumpet calls is about 2003 from Luc Rendel. In fact, it's a very rare, it's a vocal production very rare, so we don't focus a lot about this kind of sounds, but recently, especially because I have access to a large data set from François Sarano for a group of sperm whale of Mauritius Island, we just see that they use this kind of vocalizations more often than we thought. And the thing is, we have no idea how they generate this kind of tonal vocalization. So we work on it. So next year, I will tell you if I publish something about it. Okay, so we focus on codas, especially because we start a study led by José Coche Di Jacovo at Dassault Systèmes. In fact, the idea is to consider these codas as one thing, okay, and in their language. The codas, in fact, is successive clicks, but with different time between each click, like a short time, for example, a long time, okay? So we can, like a Morse, if we can do a Morse language, if we can do a parallel on this. And we were very impressed about the use of these codas for many reasons. First one, it seems that each group of social group of sperm whales use the same codas, and we can, for example, off Mauritius Island, we have the histogram of the different codas they use, and one is the main one. It's about 8 clicks, and it's different from all the sperm whales in the world. The second thing, it's the pods. We can use this information to track them during their routes, okay? And so it's what we did, what José did. So we get hundreds of different social groups in Pacific, okay, and different areas. They did the recordings on the sounds emitted by these sperm whales, okay, and we detect the codas, and after that, the idea was to use linguistic distance to track the same individuals of the same social clans. And this result is not already published. We have to work on we have to write it, but for you, just in the first result, in fact, we can have very long distance, okay, and also over years. I mean, for example, if you focus on the first of the top imaging on the left, you have the distance between Tonga Island and Galapagos, and it means that these social clans from 2003 to 2013, in 10 years, they just move from one area to another, okay? Okay, now I will switch to orcas. I was yesterday morning, early morning at the French TV to speak about the different attacks of the orcas, you know, of Gibraltar and Portugal. They tried to push a little bit the sailboats around, and 10 days ago, boats sank, and so they. Very interesting. Okay, so they have these species are very. They have a lot of different sounds, and a large repertoire from clicks, from whistles, moans, groans, and in 2000 and probably 2004 or 6, Canadian researcher. Notice that in one pod, so one family, about 10, 12 individuals, they share the same sound. So it means that they call it clan dialect. So he was able to distinguish the different pods from their emitted sounds. Okay, so we are going discretely to individual acoustic signature. I wrote it on this slide because it's a very challenging thing. About the 90 species, we speak about individual acoustic signature for probably 4 or 5 species. So we are very late on this. And I want to mention a project, Orca Slang, from a German laboratory of computer science. Why? Because it's kind of what we want to do with AI, especially, I think before these new tools, we focused on different vocalizations, but now we can process big data set, okay? So they process something like 245,000 vocalizations. So it means that we can change the scale of our approach, and we can focus on different features. And so they define the 6 main categories, and after that we can see if how the variation inside the one category, one class, what is the variation on the one class. Okay, so it means that because of these new methods are performant, we can probably go further and to focus on different details. Okay, we will start this thing with Gaël Savornin. I recruit this student. He will start his PhD next month, and we will focus on the orcas of Saint-Pierre-et-Miquelon archipelago and Newfoundland. I mean, it's on the east coast of Canada, and it's very interesting because the Canada researcher did a lot of work on the population of orca of the west coast. I mean, all the orcas in front of Vancouver to Seattle are in catalogs, and we can follow them during all their lifespan, but in the East Coast, they have nothing, okay? And when I went to Saint-Pierre-et-Miquelon in 11 and 13, we thought that it was about something like 20 to 30 orcas in this water, and in fact now we think it's about 150, so we are like not exactly in the good thing, but it's probably, it could be the biggest population of the North Atlantic Ocean. But the problem is we need to process all the data, so, and we want to combine visual observation because we can identify each individual with the mark they have on their body, and also we want to record their emitted sounds. And so we need to process all this data. And so what we did with Enstar-Bretagne, the laboratory of STIX, is to develop a website, and we invite anonymous people to come and to labelize the acoustic recordings. Okay, we ask the people to say, okay, do you in this short spectrogram, you can listen to the sound obviously, but on this short spectrogram, do you see sperm whale clicks, for example, and you have to click on it or not? Do you see some humpback whale vocalization and so on? And it works well. Okay, we'll go very fast. We switch now on humpback whales. I will go fast. Humpback whales, so since 1971, from a publication of two American researchers, Roger Penn and Scott McVeigh. It's amazing publication because it's about the song of humpback whale. Okay, and from this, with so Roger Penn, Scott McVeigh, his wife Ella McVeigh, they just noticed that this species they emit sounds, okay, vocalization, but in a specific sentence. Okay, do you want to speak humpback whales right now? Okay, let's go it. Alors, I will tell you. I will give a letter of the vocalizations. Okay, because it will be it's clear. Okay, so let's say vocalization A in two parts. Okay, vocalization A. Oh, it's the same one. So repeat vocalization A. So A. Pulse sound, that's nice. So let's say B. So it's A, B, whoop, C. B again, so A, B, C, B. T, B, B, B. And go again to A. Okay, so A will do twice. So first A, so now the second one. Okay, after that you have a B, so it's a pulse sound. Okay, after 6 and so on and so on. Okay, so now it's easy because we know the thing, but at this time it was kind of crazy. And so what we did, we worked on the vocal generator because we want to make the link between the vocal generator and the vocalization, the acoustic feature of the vocalizations. And we published something like 6 months ago, a very nice paper about biphonation. I mean, the humpback whale can do a biphonation. It means that they can produce 2 different sounds with the same vibrator. Okay? And why it's important, I mean, we don't care, but what is important, it's because we want to go to the individual acoustic signature, and this kind of specific features can be interesting for that. Okay, and we describe the behaviors, so we can make the link between some emitted sounds and the behavior. And why? Because with the electronic device we put on whales, we have the video, the footages, and in fact, like, for example, the calf is going to suckle to take milk. And in fact, before that, he emits sounds, and we published a paper about begging, so how a calf beg to just inform its mother that he wants to have milk. Conclusion, I'm not too late. Conclusion, okay, so about soundscapes, in fact, we have to measure all the ambient noise in the ocean, and especially for human activities, but also for all the marine protected area. because they want to know about what is in these areas. About the species, about the cetacean species, it's interesting to see that we already spoke with dolphins, okay? So it is clear where we can have an interaction like you do with your cats or your dog. We spoke with dolphins and we explained different things. But now we want to do the same for the different species and in their marine environment. Et voilà, to combine different methods and to communicate. Thank you for your attention.
Thanks a lot, Olivier. I don't know how to say in English, either it was a whale of a talk or a fantastic talk.
Thank you.
So we have time for questions. Maybe I'll start with one. So you're focusing on different species, but are you able at this stage to even try to do some sort of philology of the different proto-languages per species?
Yeah.
Is it possible to do that?
Yeah. In fact, it's interesting to see that their language is not the same from something like 20 years ago, 40 years ago, and now, because they are not robots and they learn from each other and they influence.
And you see the dynamic on such a short time.
Of course. And so it's interesting for example, for humpbacks. In a specific, so humpbacks, they do migration routes between feeding and breeding areas, and the male, okay, they are going on the routes, and they start to sing, and the sing will change. We change in two ways. Little change is called evolution, and a strong way is called revolution. Okay.
But you don't.
But
are you able to spot dialects or accent? Per region?
I'm sure the accent, we know that, for example, in the Indian Ocean, the vocalization is not the same as in Hawaii, for example, or North Atlantic, because
and you can pattern that, you can detect the pattern.
Okay, but, for example, the whales in Indian Ocean have the same vocalizations of whales of Angola. Okay, and the thing, it's how it's possible and so on, is because it's the same whales. Okay, they choose at one point in the South Africa if they want to go in Atlantic, South Atlantic or Indian Ocean. So we can have information about their population and about their strategy from the sounds they emit.
Amazing. Are there any questions from the room? I continue with one then.
Okay.
So you mentioned that a little bit, but how far are we? I know you specialize in underwater, but how far am I to understand my dog?
Oh yeah, but you did it all the time. I mean, you do it all the time.
With the sound, with the barking.
Yeah, you can speak to your dog, and he can speak to you, and it's totally normal, and we do that all the time. I mean, so for a wild animal, it's different because we are not totally ready to have an interaction as an interaction. And for the 90 species of cetacean, it's interesting because few of them are interested about what we are doing. Okay, so they come to us, like orcas, for example, or humpbacks, and so we can do some experiment with, or belugas, for example, we can do experiment with them. And I didn't mention it, but I was in one of my slides. We will, now we worked with amazing researchers called Charlotte Curé from CEREMA, and she do playback. Okay, and playback is what? We have an idea about a specific vocalization, for example, and we want to be sure that it's that. For example, for sperm whales, we have a specific coda to call one individual. Okay, so we want to go with waterproof speaker, put in the water, play the coda, and see if one sperm whale comes. But if it's always the same individual, it means that it's not only a call, it's a call for one individual. You see what I mean? And we go like this, step after step, step by step.
So thank you so much. At the time of the large language model era, it was, I think, very, very soothing and refreshing to see the perspective on real species language. Thank you very much. Let's give an applause to Olivier. Thank you so much.